Hi all. Before discussing questions on the gradient descent algorithm, uh, I would like to discuss a very important inequality which guarantees the theoretical convergence of a gradient descent algorithm uh, when few conditions are met. Okay, we'll discuss the conditions one by one, and we'll discuss why the conditions are satisfied by the regression problem. Right. Before that, let's see what is the context uh, of the problem. Right. We have a function f which we want to minimize over x and has a domain Rn, right? And the range of f is R. So f is like a scalar field. F is a function from Rn to R, right? Now, before that, let's also discuss the gradient descent algorithm in detail, right? It says that the k plus 1th iteration of x is nothing but the kth iteration minus the gradient of f times some vector, some value t, right, which is multiplied with the gradient of f evaluated at the kth iteration of the function value. Okay. Now, uh, again, x0, which is the initial condition, is randomly chosen. Okay. Now, this t is called a learning parameter, right? And in most cases, t is constant, but t also depends on the iteration, right? But typically, in a lot of cases, we'll see that t is independent of the iterations, right? It's called the learning rate or the learning parameter. And in this context, we will see that we'll prove the inequality, or we'll show that the inequality holds for a fixed t, right? So the inequality goes like this: the kth iteration value of the function f minus f of x star. Now, what is x star? X star is the theoretical minimum, okay, the hypothetical minimum of the function f, right? Now we know that a theoretical minimum exists, right? So one might think, okay, x star is, we do not know x star, right? That is true, but it is a theoretical local minimum, right? And we will say that the inequality holds theoretically, right? Again, f is a convex function. Okay, so what we can say about a convex function, we can say that any convex function will have only one local minima, right? And that local minima will be the global minima. Okay, so essentially the minimization of fx works. So fx star, x star is the local minima, which is a global minima in the context of convex functions, and fx star is the function value there. Okay. Now, what does it say? It says that it's upper bounded, right? The difference is upper bounded by some values, by some positive value. Okay. It means that f cannot be very large. Okay. There is some limit on how large the difference can be. So the numerator is the difference between the initial value and the optimum value, and the norm of that, the L2 norm of that, divided by 2 into t into k. What is t? T is constant here, okay? T is the learning rate, which is constant. Okay? In our case, it does not depend on k, and k is the iteration, right? The kth iteration. Okay. Okay. So that is how. So this is the inequality. Okay. Now let's start with what. So this inequality holds under some conditions, right? Let's discuss the conditions. Okay. The first condition is that f should be convex, and it should also be differentiable. So f should be convex and differentiable. Now, does this hold for our case, right? The case of regression analysis, right? So in our case, the objective function is summation of w transpose xi minus yi whole square, right? where the W is uh, the vector of parameters, right? Now we know that any y equal to x square is a convex function, and we also know that sum of convex functions, right, is again convex. So we know that a squared function is convex, and we know that the sum of convex function is also convex. By that we can conclude that the objective function is a convex function, right? It's convex and it's definitely differentiable, right? Because y equal to x square is again differentiable. So convexity and differentiability is satisfied, right? Remember, we are discussing the conditions which required to be satisfied to fulfill the inequality. Okay. The second criteria is that the gradient of f must be Lipschitz continuous. We'll discuss what that means. The gradient of f must be Lipschitz continuous. It means that uh, the difference between the gradients at any 2 points x and y. So x and y are arbitrary points in the domain of f. That should be less than equal to a positive constant L times the norm of the distance between x and y. Right? Again, L2 norm everywhere. Okay. As of now, we are only using L2 norm. What is L? L is a scalar, and L is a positive constant. Okay. It's a positive scalar. Okay. Now, what is this? Is the definition of Lipschitz continuous. Okay. And it also has an equivalent criteria. Okay. By an equivalent criteria, I mean a necessary and sufficient condition, right? For Lipschitz continuity to hold, right? So if f is C2, which means that if f has a derivative and it has double derivatives and the double derivative is continuous, right? That is what means by f is C2, and we know that the objective function is C2, right? Then the gradient of f is Lipschitz continuous if and only if the Hessian or the double derivative of f minus L times I, which is, the identity matrix, right? So both of them are matrices. The first one is the Hessian matrix, and L times I is a scalar matrix, right? L is a scalar multiplied with the identity matrix. So it's a scalar matrix. The diagonal elements are L and non-diagonal elements are 0. Okay. Now, this difference, right, is again a matrix, right? Because again, difference of matrix is a matrix, right? Now, the criteria is that the matrix should be non-negative definite. What does that mean? That means that all of its eigenvalues should be negative or 0. Okay, it can be 0, but it cannot be positive. Okay. That is the criteria. Right? Now we will show. So what can we say about our objective function? Right? Is it Lipschitz continuous? Right. So our objective function is xw minus y norm squared, right? Which is nothing but xw minus y transpose times xw minus y. Right? Now, the gradient of the objective function would be, let me expand this to w transpose xw minus y transpose xw minus w transpose xy plus y transpose y. So the gradient is nothing but the derivative of the objective function with respect to w. Right? Again, w is a vector, that's why we have a gradient. Now what will this be? This will be 2 times x transpose x into w minus x transpose y minus x transpose y again. Okay, so this would be nothing but 2 times of x transpose xw minus 2 times x transpose y. So this can be found in any standard textbook. How I could differentiate the function, with respect to the vector. This is quite straightforward, and it can be easily found in uh, it can be found in Wikipedia or in any standard textbook. So now we have to look at the double derivative of the objective function with respect to w, right? Or the Hessian, right? Which will be a matrix, right? So the double derivative with respect to w2 will be the Hessian of the objective function. That will be 2 times of x transpose x. So now we know that uh, if you take, so what we need that this criteria to hold, right? So we need that we choose L to be 2 times of the maximum eigenvalue of x transpose x, right? Now how does that help? We know that the eigenvalues of x transpose x will be of the form, say, lambda 1 greater than equal to lambda 2 greater than equal to lambda 3 and so on, and some of them can also be 0, right? But we know that there cannot be any negative eigenvalue, right? So since it cannot have any negative eigenvalue, we'll take the maximum, which we denote by lambda 1, and our required capital L, or the Lipschitz constant, is 2 times of lambda 1, right? Now if you look at the difference between the Hessian and the scalar matrix with all diagonal entries being L, right? What can you say about the eigenvalues? It will be of the form 2 times lambda 1 minus lambda 1, 2 times lambda 1, 2 times lambda 2 minus 2 times lambda 1, 2 times lambda 3 minus 2 times lambda 1, and so on, right? Now all of this will be less than equal to 0, right? All of them will be. So all of them are negative definite, or you can say semi-definite, semi-negative definite, right? So this is a semi-definite, semi-negative definite matrix, and that is so the second criteria is satisfied, and the first criteria is also satisfied, right, for our objective function. Okay. Now there is a third criteria. So basically, what does this inequality say? The inequality says that the difference is upper bounded, right, by some value, and we have t and k in the denominator, right? Which means if you increase k, the bound will decrease, right? The difference will decrease. That's what it means. Now, what is t? Right? T is important. Right? Now, t here is the constant learning rate. We have one more condition which is on t. Okay, let me write it here. So the third condition says that t should be less than equal to 1 by L. We know what L is. So now we can assure that t is less than equal to 1 by L. 1 by L. Now this should trigger something. Why? Because you must have seen in standard textbooks and maybe in other courses that if the learning rate is chosen to be very high, right, then sometimes the gradient descent algorithm does not converge, right? And this is exactly the reason why, right? Because for this inequality to hold, or for the convergence to actually happen, t should be small enough, right? If t is too large, then the convergence might not hold, right? So this is one of the reasons why t is it fails when t is too large. Okay. All right. So we've discussed 3 conditions, right? And we can see that the conditions are satisfied by the objective function in our regression analysis case. And we saw why we have an upper bound, and this upper bound says that the difference between the kth iteration function value and the minimum function value cannot be too large. Now, one more thing to notice is that to compute the derivative of the objective function, we need to compute this particular value. So essentially we need to compute x transpose x. Now if the data set is very large, right, this becomes very computationally intensive, right? This always is very intensive when it comes to computation, right? And that becomes a challenge, which means the learning will be very slow. Okay, it also means that the learning will be very slow, right, when you have a large data set. Okay. All right. So these are few takeaways. Now, one might argue that since the numerator is already there, so one might think that the numerator is a positive value, and what if the numerator is very large, right? But even if the numerator is very large, say for example, I take the numerator to be 10 to the power 6, it's very large. Still, we can choose k to be larger than that, say 10 to the power 60, right? In that case, again, the upper bound of the difference becomes very small, right? So that's how we can ensure that theoretically we can have an upper bound, right? So definitely we cannot run it for 10 to the power 60 iterations, but theoretically we can show that it can be made to converge.